Hi kids, in this video we are going to start laws of motion from class 9 physics. The first thing we need to define is force. How do you define force? Now in our previous classes you may have heard force is a pull or push. Now we move ahead. How can we define force over here? Just look over here, a broader picture. Force is a physical cause that changes or tends to change either the shape and size of a body or the state of rest and motion, state of rest or state of motion of a body. So this is how we define force over here. A certain key points to remember over here in the definition. First of all, it's a physical cause. Second, it changes, there's one more word, tends to change, which means these changes, change in shape and size, change in state of rest or motion may happen, or at times it may not happen also. Changes or tend to change. For example, imagine me if there's a train at rest and I'm trying to set the train at motion by merely pushing it. I won't be able to do. Though I'm applying force, but I'm not able to change its state of rest. So either it changes the shape and size, which means it changes the dimension, you can say, of the body, or the state of rest and motion of a body. So from here, from this definition, we can actually get the effect of force. Look carefully. Effect of force, one by one. First look, changes the state of rest, which means if a body is at rest, it can set the body in motion. For example, due to Earth's gravity or Earth's pull, the apple falls down, isn't it? If suppose you're playing football, if the football is at rest, you can set the football in motion by merely kicking it, by applying force, isn't it? First effect. Second, it can change the state of motion of a body. Now, state of motion can be divided into many parts. First, if the body is in motion, we can bring the body at rest. For example, if you play cricket, you must have seen the fielder stops the ball by applying force from his hand. So the ball was in motion, its state is changed from motion to rest. Next, we can change the speed of body in motion. Speed of body can be changed in motion. You must have seen, if you drive a cycle, by applying force on the pedal, if you increase the force, you can change the speed of the cycle. A freely falling body, you see, the speed continuously increases due to Earth's pull. There what happened? The speed of the body is changed. In football, cricket, hockey, you can change the speed of the ball, isn't it? Number 4. You can change the direction of motion of the body. For example, you must have seen, again, when you play cricket, the batsman hitting the ball, and what it does, it changes the ball's direction. In hockey also, suppose you tie a stone with a string and whirl it in a horizontal circle, what happens? the direction of motion changes due to the tension on the string. We will discuss about tension in detail. That's a type of force, Then we can change the shape and size, which means we can change the dimension of the body. We can change the shape and size. For example, when you press a rubber, what happens? The shape of the rubber changes. When you stretch a rubber band, the length of the rubber band increases, isn't it? If you see in a pressure cooker, steam coming out of the cooker, in the atmosphere, its volume increases, isn't it? For example, when you pump air in the cycle, when you press the piston downward, what you are doing? You are compressing the air, the volume decreases. So these are the effect of forces. Now, one more thing we need to remember here. What happens when force is applied on a rigid body and a non-rigid body? First of all, what is a rigid body? See, a rigid body is the one in which if you apply force, you can't change the interspace between the particle. You can't change that. Which directly means you can't change the dimension of the body. By applying force, you can't change the dimension. So what you can do? You can bring motion in it. You can bring motion in it. Is it clear? But when you talk about a non-rigid body, you can change the interspacing or the interspace between particles, which means you can change the dimension, the shape and size of the body, can change the dimension of the body. So when force is applied on a non-rigid body, you can change the dimension as well as you can bring motion in it. So these things we can do. Am I clear? So this was the effect of force and what happens when you apply force on rigid and non-rigid body. Now let us see contact force and non-contact force. Now from the point of view of application, the forces are classified as contact and non-contact or forces at a distance. Forces at a distance. Now what do you mean by contact forces? The forces which are applied on bodies by making physical contact, with them, which means the bodies are in contact with them, is known as contact forces. And what is non-contact forces? Forces experienced by bodies when they are not in contact, when they are not in contact with each other. Over there the forces, if there exists a force, that is known as a non-contact force with each other. Now when you talk about contact forces, we have different types. First is, you can say, tension by a string, that's a force. Frictional force, these are all examples of contact forces. We'll do this, okay, one by one. Frictional force, then normal reaction force, force exerted by a spring, force due to collision of two bodies. Force due to collision. So these are types of contact forces. Non-contact forces, when you talk about, we have magnetic force, okay, we have electrostatic force, and we have gravitational force. So these are my contact forces, these are my non-contact forces. Now let us look at each of them separately. Now let us discuss frictional force first. Very important. What do you mean by frictional force? So when an object slides or roll on a rough surface, suppose I take an example. Suppose there's a body A, it is kept on a surface, and we are applying a force F, capital F, to move this object towards the right side. Then what happens? Then an opposing force, a resistive force, FF I've written, which is known as frictional force, acts in the direction opposite to the direction of motion of the body along the surface in contact, and it's a resistive force. It resists the motion of the body, which means we can say, what is frictional force? It is a resistive force. It tries to slow down the motion, resist the motion, resistive force. It always acts in an opposite direction to the motion of the body, acts in opposite direction to the motion of the body. Then you can add one more point. It acts along the surface in contact. So this is my frictional force. This force acts whenever a body slides or rolls on a rough surface. And since it is, see, it is in opposite direction to the motion of the body, it tries to slow down the motion, tries to stop the body. That is my frictional force, resistive force. It resists the motion. Clear? Now let us see normal reaction force. Now suppose you have a table and you have kept an object over it. Now the weight of the object acts vertically downward. The weight of the object acts vertically downward, but still the body does not falls or move. Why? Why does not fall or move? Because there is an equal and opposite force normal to the surface. What happens? This weight is balanced by an equal and opposite force normal to the surface. That is known as my normal reaction force. Suppose R. So what is normal reaction force? It is equal and opposite to the weight of the body, you can say. It is normal to the surface. It acts normally to the surface and in opposite direction to the weight of the body. It's in equal and opposite to the weight of the body and acts normal to the surface. Suppose on your palm, I know my diagram is horrible. Suppose you place a object, a cube. Then what happened? The weight of the cube acts downward, which will try to lower your palm, but what happens? If we try to keep it in the same position, what we are doing? We are applying an equal and opposite force to the weight of the body, which is known as normal reaction force. It is equal and opposite to the weight of the body, and it is normal to the surface. This is the reason why the object does not fall or move, due to this normal reaction force. Now let us see the next one. Now tension force as applied through string. Now take a rigid support with the help of a string. If I suspend a body, then what happened? Due to the weight of the body pulls the string vertically downward. In that scenario, the string pulls the body vertically upward with a force equal to the weight of the body known as tension, which balances the weight of the body, which means in equilibrium, tension of the string will be equal to the weight of the body. Am I clear or not? So in equilibrium, you can say tension is nothing but the weight of the body, then opposite direction. Okay. Now look carefully. Suppose the object is over here. You cut the string from here, just above the point of contact. Then you see this string moves upward with a jerk. Moves upward with a jerk. Why? Because of the tension. This tension pulls the string upward. But later you see that it falls down. It comes down. Why? It comes down due to the gravitational pull, due to the weight of the string. It comes down. Then it comes down due to the weight of the string. Am I clear? Just remember, in equilibrium, tension in a string is equal to the weight of the body, which is hanging with the help of that string, or suspended with the help of that string. Clear? Now let us see the next contact force. Now force exerted by a spring. Now consider a case where a spring has one end fixed to a rigid support. Now, if you try to compress or stretch, suppose I'm stretching it, I'm increasing the length, stretching, or you try to compress the length, compress the spring, then what happens? A restoring force develops in a spring opposite to the direction of displacement. What? A restoring force develops in the spring opposite to the direction of displacement. Am I clear? Just look, the body is displaced over here. So a restoring force acts in this direction to restore the spring to its original position. That is why it is known as restoring force. If you leave the force over here, if you stop pulling it, then what happens? It goes back to its normal position. If you leave compressing it, then what happens? It goes back to its normal position. So that is why it is known as a restoring force, that is opposite to the direction of displacement. Am I clear? And the magnitude of the restoring force is directly proportional to the displacement, which means if you stretch more, if the displacement is more after stretching, then the restoring force, the magnitude of the restoring force will be more. If you stretch less, then the restoring force will be less. Spring balance, spring balance works on this principle only, spring balance. Am I clear what is restoring force exerted by a spring? Take one more example. Suppose you have two bodies, A and B, connected by a spring. This is the normal position. Now when you compress it, then the restoring force will be in this direction. It will try to push the two objects. After compressing, what happens? There will be a restoring force developed in the spring which will try to push the two objects away. But if suppose this two are your object A and B, and you try to pull them apart, then what happens? The restoring force acts in this direction, will try to pull them back towards each other. Am I clear? Just remember, it is opposite to the direction of displacement and its magnitude is directly proportional to the displacement. Okay, now let us see one more contact force. The force exerted during collision. Now when two bodies, in this case I have taken A and B, when they collide, they push each other, as a result of which equal and opposite forces act on both the bodies. These are your force of action and force of reaction when they collide, and they are equal and opposite to each other. Suppose what happened when they collide at that point, when they meet each other, when the collision take place, then what happens? This is your body A, this is your body B. Then the body A applies a force FBA. FBA is what? Force on B due to A. It applies a force on B. Similarly, this is suppose the force of action. Similarly, what happens at the same instant? What happens? The body B, applies a force FAB on A. Force on A due to B. This is reaction force. If this is your action force, and if you take this as a force of action, this becomes your force of reaction. This happens at the same instant. So whenever two bodies collide, there's a force of action and reaction which pushes them. Am I clear? So after collision, what happened? See, after collision, what happened? They'll move like this. Suppose this is your body A and this is your body B. This is before collision, at the time of collision, and after collision. Am I clear? So there is a force of action and force of reaction during the collision of two bodies. So these were my contact forces. Now let us discuss non-contact forces. The first one is your gravitational force. The first one is your gravitational force. Now in the universe, each particle attracts other particle due to its mass. That force, that attractive force due to which the two particles are attracted towards each other, that is known as gravitational force. And over here what I have written? Attracts, which means this force is attractive in nature. This force is attractive in nature. First of all, gravitational force is always attractive. They don't repel. Like in magnets, we have attractive force as well as repulsive force. But in gravitational, it is always attractive. It's a very weak force. It's a very weak force. It depends on the mass of the body. And it also depends on distance of separation of the body. Now, Earth also, see, your Earth, due to its mass, attracts object around it, and that force is known as force due to gravity. Force due to gravity, which is equal to the weight of the body, isn't it? Which causes, and this force due to gravity causes motion in a body downward if a body is free to move. If a body is free to move, is due to this force of gravity that if I leave this pen, it falls downward because the earth attracts this body. Now you can say that the earth attracts the body, so the body goes towards the earth. But the body is also attracting the earth. But there's no motion on the earth. The earth does not move. Why? Because of the large mass. Because of the large mass of the earth, the earth does not move towards the body. The earth does not move towards the body. Both are attracting each other by equal force, But due to the mass of the earth, which is too much, there's no motion in the earth. Now, there are a lot of examples of this. For example, if you place a ball on a table, and you tilt the table a little bit, what happens? The ball slides down, okay, due to the force of gravity. If you leave a coin, what happens? The coin falls down due to the force of gravity. If I throw a ball up, vertically up, what happens? It goes up. At a certain point, it comes to rest. Again, it is attracted downward. It falls down due to Earth's gravity. So that is your gravitational force. Always attractive in nature. Clear? Now, let us look at the next non-contact force. Now, let us see electrostatic force. Electrostatic force. As the name says, electrostatic means a charged body. The force developed due to the charge of the body. Force developed due to charges present on the body. That is electrostatic force. It is both attractive as well as repulsive. Take an example. Take a body A, take a body B, separated by some distance. Suppose this is a positive charge body, this is a positive charge body. You will see that they repel each other. There is a repulsion because of like charges. If you take, suppose, another case where you take a positive body and you take a negative body separated by a distance, you will see that they attract each other. They attract each other due to unlike charges, which means the force is developed due to the charge present on the body. That force is known as electrostatic force. It can be attractive as well as repulsive, because in gravitational force it was always attractive. Now, a very simple example, we can do it in our house also. Suppose you take a comb and you rub it against your hair. Then what happened? Due to the transfer of electron from the hair to the comb becomes negative charge body. The comb, suppose this is my comb, this becomes a negative charged body. Then when you bring this comb near bits of paper, then the opposite charge is induced in the bits of paper. Opposite charge are induced, and this causes attraction. So the bits of paper, you see, gets attracted towards the comb. That's an example of electrostatic force. Over here it was attractive in nature. Done. There is one more. Now let us see magnetic force. What is this? Very simple. The force between the magnetic poles is known as magnetic force. Simple. Suppose you take two bar magnet. Suppose this is north pole, south pole. We have done. A magnet has two poles at its end, north and south. And suppose we have another magnet, bar magnet, south pole and north pole. If they are at a distance, if the south pole is brought towards the south pole, we'll see that they repel each other due to like poles, like the like charge, But if you take a magnet, bar magnet, and bring opposite poles, you see that they attract each other due to unlike poles, which means unlike poles attract each other, alike poles repel each other. Clear? Now you must have seen that a piece of magnet attracts iron nails. How does it happen? Because what happens, the magnet induces an opposite polarity at the end of the nail. So what happens, the nail gets attracted towards the magnet due to the magnetic force of attraction in that case. And again it can be attractive as well as repulsive, based on which two poles are brought together, are brought near to each other. Now some general characteristic of non-contact force. First thing is that they are attractive, like in case of gravitational force, magnetic force, electrostatic force. It can be attractive as well as repulsive. Attractive is only in case of gravitational force. Gravitational force is always attractive in nature, but when you talk about magnetic force or electrostatic force, they are both attractive as well as repulsive. Second, this force depends on this non-contact force depends on the distance of separation. It is inversely proportional. This force is inversely proportional to the square of the distance of separation, which means if you increase the distance between the two objects twice, suppose double, if you double the distance, then what happens? The force becomes 1/4. The force becomes 1/4 of the original case. If you double the distance between two bodies, the force becomes 1/4. So these are the general characters of non-contact force. Done. So in this video, keep it till here. In the next video, we'll see the other portion of this chapter. Till then, take care and be safe. And if you like the video, do subscribe.